Hello everyone, a very good afternoon. Welcome to today's webinar titled Automotive Testing Lessons from Data Storage Industry, featuring Quarch Automotive Solutions. A warm welcome to all our attendees from the entire teams at Electro Systems Associates, ESA India and Quarch Technology. While we have attendees joining in, we'll get started with a brief introduction to the panel and the parties hosting this webinar. I'm Pratibha Gopalam, the Executive Director at Electro Systems Associates, ESA India, and Gopalam Embedded Systems, GS Singapore. From the ESA group, I also have Mr. Pasha, General Manager Sales on the panel. Today from Quarch, we are very pleased to introduce Mr. Andy Norrie and Mr. Laurie Samuel. Andy is the co-founder and CEO. Laurie is the International Business Development Manager. ESA and GS, the ESA group companies, are Quarch's local partners and representatives in India and Asian region. We are responsible for promoting Quarch solutions in the regions, managing customer requirements, also sometimes developing custom solutions, sales, training, and support. In today's webinar, specifically, we will be presenting Quarch's automotive test solutions, addressing the critical importance of vehicle communication reliability and power analysis in automotive systems. Also, if you're wondering about the mention of data storage industry in the title, a little bit of background. Quarch Technology began as a leader in automated test solutions for the data storage industry, quickly becoming the gold standard for reliability testing and power analysis for SSD and other storage devices. Their tools are widely used in data centers and major storage manufacturers, enabling very rapid, repeatable, highly accurate testing for critical interfaces like PCIe, NVMe, and CXL. Over time, Quarch leverages expertise in physical layer testing and power analysis to expand into the automotive sector, where similar challenges such as reliability of high-speed communications, validating power consumption, and fault injection are all very important to modern vehicles. In the session today, Andy will be highlighting the need for reliable physical layer testing and fault injection in vehicle communication networks and power analysis solutions for automotive systems. He will be presenting some very interesting and critical use cases, followed by detailed explanations of the available Quarch solution. The first main use case would be testing of high-speed vehicle communication networks and automotive interfaces. As vehicles become very connected and autonomous, the performance, reliability, and the interoperability of communication networks such as CAN, LIN, Ethernet, and other serial protocols directly impacts vehicle safety, functionality, and user experience, performance, amongst many other things. If you're in this space, then you'll definitely find the Quarch automotive multi-protocol breaker extremely apt and exceptional. The second main use case will be the power analysis of automotive subsystems. If you have been struggling with high-end oscilloscopes, bench power supplies, power meters, multiple probes, then Quarch offers a remarkably simple, easy to use and highly economical solution. Their compact, easy plug-and-play power analysis solutions will deliver very reliable and precise measurements without the complexity and the cost of traditional instruments. Okay, so again, power analysis is very critical in the context of EV charging, battery technologies, and motor systems because again, it impacts efficiency, safety, and performance. The third other interesting use case would be testing of USB interfaces. Again, testing of USB interfaces in automotive infotainment systems is very essential, ensuring reliable connectivity, safety, and user experience. We all know in modern vehicles, we rely on USB for critical functions like smartphone integration, media playback, voice assistance, fast charging. So robust testing of this interface is also very, very important. For this, Quarch offers both the hot plug and power analysis solutions, which Andy will be presenting. So this is, I just wanted to give a brief overview and a context. Now we will get started with the main session. I would like to invite Andy, who will be our key presenter today, to start the session. I will be helping in moderating the session. We will also be making the session very interactive. We'll run a few polls. We'll be taking questions along the way instead of waiting till the end of the session. So please leave your questions, as many as you want, in the chat box. We'll try and take most of them in the session today. If we can't get to everyone, then we will reach out to you offline and provide all the necessary support. Also, please note this webinar is being recorded. If you need it to be sent to you, please send us a request. Andy, we welcome you to begin the session.
Thank you very much, Pratibha, for the introduction, and thank you all for joining us. So first, I'd like to just tell you a little bit about Quarch as a company. Although Pratibha's given us a very good introduction already, I appreciate that. We've worked together for many years now in India. So Quarch was founded in 2006. We're a relatively small team, but we've got over 20 employees now. We are entirely based in Scotland, in the United Kingdom, but we're also part of the larger ELYSIS or symbiosis groups that you may know from other areas such as Bluetooth analyzers. We've got high quality partners in every region, including ESA, of course, and we got a very good reputation with our customers. We offer a lot of direct engineering support, and in our traditional data storage space, we work with basically every major storage company. We've contributed to a number of industry specifications with the Open Compute project and SNIA in terms of energy efficiency and automated testing. So while we may not be a familiar name in the automotive industry yet, as I say, we're well known in data storage. Now, the reason I really wanted to speak about this with you today is because there's quite an overlap now. It might not be an obvious one from the outside, but more and more technology has obviously made its way into automated vehicles, whether it's attempts at full self-driving or whether it's integrated cameras, ADAS systems, or just fancier infotainment. We are seeing most of the elements you'd expect to find in a data storage system migrate into a vehicle. These include, obviously, CPU compute. So compute within a vehicle has massively increased in the last 10 years or so. We're also seeing GPU-based compute in terms of AI image recognition. Data storage, that being our key industry, of course. We have worked with devices from the days of SATA through SAS, NVMe, and the more modern OCP and CXL devices for super high-speed storage and memory. Now, not all of those have made it into vehicles yet, but automotive SSDs are now a full category in their own right. There is more and more storage in a vehicle, and of course, it needs tested. Next, of course, are the data links, the key parts that join the elements of the system together. In data storage, PCIe is one of the biggest, with Ethernet then connecting major sections of racks and similar, and newer systems like CXL for high-speed memory. Many of these are found in vehicles as well. There's some differences. You have a lot more CAN and similar, but Ethernet is in vehicles. USB is very common in vehicles, of course, and we're seeing a number of technology companies pitching PCIe interconnects within vehicles as well. The main difference really is what the data is used for. The reason our customers have to do a lot of testing in data storage is because they are processing critical data, and often done in a time-critical way. So if a rack of servers goes down due to an error, it's a critical problem in the finance or health industries or whatever it is they're serving. In a vehicle, it could be crashing into a lamppost. It's a safety-critical thing. So, as I'm sure you know, a huge amount of testing has to be done. And what we're interested in sharing today is how some of these problems have been solved in data storage and how they could be brought into the automotive testing domain. So the first one we're going to look at is fault injection.
And
so this
can we just run the poll, please?
Sure.
Yeah. Yeah, and I'm sorry, I just got feedback that my voice was breaking. I am on a better communication. I mean, I'm on a better link now, so we should be better. So we'll just run the first poll. It's coming up. We request all the attendees to please participate in the poll because it gives us good feedback. It also helps us understand what is the focus each of you has in your testing initiatives. So this is the question: what is your biggest challenge in testing automotive communication reliability? The options are testing multiple links, CAN, LIN, Ethernet, USB, PCI, injecting repeatable faults, complex or time-consuming setups, presently not working on any of this testing.
This is really useful feedback in what I talk about.
So we're just going to run it for 10 more seconds. Please, we have nearly about 100 attendees. So if you can give us feedback, that would be really nice. Yeah. So we'll stop the poll at this time. Andy, I will just help you with the results.
I can see them there actually. They're on the screen.
Okay. Yeah. So just the benefit for everyone on the session, we have about 52% of our attendees testing multiple link types, 16% of them who are very interested in injecting repeatable faults, and 19% of them thinking that, of the opinion that they are quite complex and time consuming. So that's the result of the poll, Andy, and I'm sure it'll help you while you move forward with your presentation.
Great. No, it's good to see we've got a good set of people here that are clearly interested in communication. So first thing I want us to consider is what links are we targeting? Now, I've selected a number of communication links that I'm aware of in modern vehicles. If you have other ones that you'd like to test, maybe you can pop that in a message to Pratibha as well, and we can talk about them later. But regardless of what technology is actually carrying data in the link, the questions I think we have to look at is, what does the link carry? What is the data? How important is it? And what happens if that link fails? And the failure could be a brief corruption of one packet of data, or it could be a hard failure of the whole link. What effect of that is it going to have on the customer's experience in the vehicle? What effect is it going to have on safety? Now, there are a number of fault injection options when it comes to looking at a protocol link. The first, of course, is protocol level injection. So this involves a protocol analyzer or jammer, or a network latency emulator is another form. So all of these work in a similar way, though. They have to read every single bit of data that comes through the link. They have to be able to process it in real time and then modify it in some way. Now, in the case of a network latency emulator, that it may just be delaying packets by a few milliseconds. In the case of the protocol analyzer or jammer, it can be flipping individual bits in a message to create a very specific error. So these are extremely detailed tests that you can perform, but they are very expensive pieces of equipment, especially for high-speed communication links like Automotive Ethernet and PCIe, and they can be extremely complex to use. We frequently have customers in the PCIe space who will buy a $500,000 analyzer, and there's maybe only one or two people in the company that can use it. So it can be very useful for testing specific cases, but it's hard. Another option we see a lot of in the automotive side is EMC-based injection. So this can be conducted or radiated injection into the system. It could be a simple ESD discharge gun. In any case, you're effectively brute forcing a zap of energy into the system to disrupt communication. It's relatively cheap, it's relatively safe and easy to do. It can be very hard to target faults though. It can be useful because, of course, we have a lot of electromagnetic interference while driving in industrial environments. It can be good testing to do, but the energy is very hard to target at specific wires. It can have a very varying result depending exactly how it couples into different parts of the system, what other metal elements are nearby. So it's hard to get repeatable results. Now, another option is direct physical layer injection, so physical isolation of the signal path. Again, this is relatively cheap and easy. It is much easier to time precise faults, and you can target one specific wire in a multi-wire link. The results, therefore, are much less variable. They're not completely repeatable, however, just because you can create for instance, a very precise 100 microsecond break in a physical interface link doesn't mean that you're going to hit the same point in the data. If no data packet was passing at that point, nothing would happen, for example. But it is a much more repeatable test, at least. And the interesting thing, I think, is in our previous data storage industry, the racks of servers are in environmentally controlled areas. They don't move, and they have a fairly limited shelf life before they're replaced. Vehicles, however, they get very hot, they get very cold, they're bouncing along the road all day, and they age very significantly. Old vehicles will continue for 10 or 20 years in many cases. Storage systems do not have many of these challenges. So communication links will glitch out and fail at some point. The question is, have we tested everything and are we ready for when that happens? So here we get to a real example. This is the Quarch multi-protocol breaker wired directly between, and we wire it directly between a host and a device. There are simple screw terminals on the front to wire in. In the example we're going to see is an automotive Ethernet. We apply power to the breaker module, 12 volts as you'll find in a car, connect USB or Ethernet to control it, and we're good to go. This can be set up in a few seconds. And what we've got here is a live demo we had from one of our trade shows recently. In this, we've got the Quarch breaker in the center of the screen. We have a pair of 1000 base T automotive Ethernet adapters on the sides. And through that combined Ethernet link, we have connected an IP camera on the right to the test PC on the left. Very simple setup, but it demonstrates an equivalent of an IP camera running in a vehicle. So let's see what happens. We're going to wave our hand in front of the camera is functioning, everything is smooth, and then we're going to run a simple Python script that activates the glitching sequence. And oh dear, immediately we're seeing lost frames, we're seeing smearing. It's quite intermittent. Sometimes the camera will hang for almost a second or two. Sometimes it's relatively clear, like there's almost nothing there. Now we are injecting a series of short glitches into the physical layer of the Ethernet link. And what that's causing is packet loss. However, the Ethernet link is very robust. The packets will either be resent, or in this case, however, the receiver will reconstruct the image to the best of its ability. But in this particular case, we are not using a TCP style system where packets are guaranteed to be resent every time. So we're actually losing keyframes. The camera quality massively drops when the faults are being injected, but no errors are raised. There's no indication on the camera that there's a fault, and there is no indication in the camera software that anything is going wrong. But we can clearly see the camera quality is unusable when that disruption is running. Now that's really interesting to me. It's unsurprising in this case that a simple streaming camera doesn't feel the need to indicate that there's a problem on the link we have to deal with. The real question we have to ask is, if we wire this into an IP-based or Ethernet-based device in your vehicle and inject those same errors, will the vehicle indicate a fault and shut down safely? Because clearly, if this camera was feeding into an ADAS system or any form of critical system for data, those packet losses could cause a crash or a serious failure of some kind. Now, there are a number of different ways that we can inject faults. In this example, we were going into a simple cabled interface. That particular breaker module we can inject into CAN, LIN, I2C, USB 2. We can do a range of serial protocols as well as the automotive Ethernet. There are 4 individual signal wires that can be individually controlled and 1 power rail, so we can cut power to a powered interface as well. But in many cases, testing has to be done before you have a completed vehicle. In a lot of cases in the storage world, for example, our customers will place devices into R&D test boards of some kind as a test bed. So we have breaker modules, for instance, for PCIe slots, for M.2 devices, for automotive SSDs, also for high-speed Ethernet, for example. So we can do well above the 1 gig automotive Ethernet. We can do 10 gig, 25 gig and beyond as well for high-speed interfaces. We can also, if you have a problem that isn't handled with one of our existing breaker modules, we can do small run custom hardware to integrate into a proprietary system. Now, what's inside a breaker? So the idea of these products is that they control the whole interface. So we can control high-speed data signals, we can control digital sidebands, and we can control power rails. If there are differential high-speed signals like there would be in PCIe and Ethernet, we can control each individual side of the differential pair. And it's just a little block diagram in the top right, shows that our device goes between a host and a device. We place individual switches on every pin of the connector, and in some cases those will be high power FETs, electronic switches for power control. In some cases there will be specific high-speed RF switches as is required to run the data, but this is completely passive. So your host and your device speak together with no idea that the Quarch breaker is in the link. It will run as normal until we choose to open one of these switches, either permanently to create a hard failure or very briefly to create a glitch. So we can do everything from making and breaking the link. We can simulate a fast versus slow connection. We can simulate things like contact bounce. So when things plug together, for instance, plugging a USB device into a port, you don't get a smooth connection. We get a series of bounces, and we can simulate those high-speed bounce patterns as well, as you can see on the bottom right. Glitching, however, is one of the key things here. This is how we generated the failures in that video before. We can glitch high-speed data rails down to about 50 nanoseconds on most devices. So on a high-speed PCI interface, it might be a few bits of data that we take out with a single glitch. But this is a very good simulation of what a vibration-induced failure on a poor wiring loom or connector is going to do. And we can create a single glitch, or we can create a cycle or a random sequence of glitches on the link. And that's what we were using on the previous video. It's also very easy to automate. So quick Python scripts can be knocked up by junior engineers in a matter of minutes that create these different failures. And it's a modular system, so it can be expanded to run across multiple interfaces very easily. And really that covers the basics of the breakers. So Pratibha, do we have any questions from that side?
Yes, thank you. There are a few questions. I'm just going to, take them together. So the question saying that we just spoke about automotive Ethernet. Do we also support CAN FD as an interface? So maybe you can elaborate or reiterate all the interfaces we support. Why don't you take that question? There's some other questions. Maybe I'll ask you after that. Yeah. Sure.
So yes, we support CAN and LIN. Again, if you look at the top left there, we have quite a list of protocols that the multi-protocol breaker can support. It's basically within a set of speeds and electrical characteristics. So if there's a specific interface that you would want to instrument that we don't have here, then that's one that we can discuss quite easily. Or it may be that we already support it on one of our existing modules, but we just haven't thought to advertise it as one of the protocols we use.
Okay. There's also questions around how do we automate it? What is the scripting support? How do I integrate with other automotive test systems?
So I will cover automation a little bit later, but basically if you can write a Python script or access a serial port, then you can automate. Our command set is very simple and it's very open. We've had to do the same thing in the data storage industry, where everyone has existing automated test systems. Quarch primarily sells the hardware. We sell the hardware and a simple interface to control it, and you integrate it into your existing setup easily.
Okay. There's also some questions about the ability to manipulate packets. I think maybe you need to clarify again that the focus here is on the physical layer testing. And there's an additional question about power consumption. Yeah. How do you power these units is the question.
So this specific unit we looked at, the multi-protocol breaker, can be powered very easily from 12 to 15 volts DC. So it can be plugged into a standard wall power supply from AC that we supply with it, or if it was within a test vehicle of some sort, it could be powered directly from the 12-volt power.
Okay. I think we can take the rest of the questions later. Andy, we can move to the next session. Or do you want to run the? We'll run the poll and be quickly. Okay. Yeah.
Sounds good.
So, dear attendees, we are running another poll. Please help us with the responses. The question is, which power behavior is most important for you to capture today? The options are fast transients, short spikes, long duration profiles, multi-rail correlation, low power states, and if you're not measuring any power at this moment, then you can pick the last option.
That's a nice spread again. So this is interesting. So power analysis, of course, is very different from what we've just been talking about. But it's another key one that I think is very important within vehicles.
Yeah. So we'll give the attendees a couple of more seconds and then we'll stop it. Yeah. So just for the benefit of everybody else who's on the session, we had about 46% of the attendees saying that the most important behavior is fast transient and short spikes. About 20% said long duration profiles, they would like to measure it over hours to days. And then about 11% say that they're interested in multi-rail correlation and also then low power states. Yeah, Andy, over to you.
Great. Okay. So first question that we need to ask when it comes to power is, what do you need to measure? There are a lot of things on a vehicle that consume electricity in one form or another. So let's look at a few of the options. A very clear one, of course, these days is EV charging. We've got 1 or up to 3 phase AC. We've got high voltage DC charging. We've got concerns over startup and inrush as the charge cycle starts. But then we've got the full charge cycle, which might run for many hours. And one thing I want to talk about throughout this is that detailed traces tell a story. There's a lot more to power analysis than just the number. We're charging at 10 kilowatts, we're charging at 20 kilowatts. A detailed trace can tell you a huge amount. And just this little example I have on the bottom left here from a simple capture of an EV charging cycle is the 3 different phases, starting 1, 2, 3 as we go through. So the phases are being deliberately staggered by this charger to start up at different times. And it's just slightly interesting to me that the difference between the first and second phase is shorter than the time between the second and third phases. It doesn't matter in this case, but every trace virtually that we take has some interesting questions around it. Why does it do that? And we find that power analysis gives you a very interesting insight into what your device is doing that you can't see by other means in many cases. Automotive SSDs, so these are a big thing, or other M.2 devices. We've said already that it's an entire market now for automotive form SSDs. You can be interested in power versus performance. How much energy are you consuming for the performance of your storage device? On the other hand, you can be looking at voltage margining. How tolerant is your SSD of different voltage levels being supplied to it? Again, this is a vehicle. It's not a data center in a perfect state. Voltages may vary for various reasons. How does the device handle ramping, glitching, brown out of power, hard crowbar short tests? Is it going to survive? If somebody drops a spanner in the wrong place during maintenance, will that kill the drive because it's gone out of its voltage rail tolerance and damage something, or will it start up happily next time? Looking at it the other way, what about the voltage stability of the vehicle? What are you supplying to the SSD in practice? How much peak power does one SSD take in comparison to another? And of course, what about low power states? In the lowest power shutdown state, how much power is your device going to use? Because that will have an effect on battery life. On the bottom, we've just got a couple of little pattern graphs which were used in data storage tests. Most SSDs these days have two different power rails, or many do. So we will have ones that have a 12 volt and a 3.3 volt rail. And these examples are showing us running different patterns on the device. So on the left, we are aggressively pulling down the voltage rail on each different power supply for a short period of time at different times. And on the right, we are simulating a ramp up of the voltage rail, but we're also simulating other high current devices coming in at the same time and dipping the voltage rail briefly. And again, we can use that test to confirm that our device is going to power up correctly every time, regardless of what else might be happening around it. Not everything, however, has a simple interface that you can get into with a fixture. A lot of, again, early testing is going to be done on R&D boards. You might be interested in testing a specific PCB consuming power, or a specific integrated circuit of some sort, or a wiring loom within a vehicle. So we have multiple options for that. You might be looking at total power consumption. You might be looking at multiple rails that you want to look at together. Internal rails within a test board can need more effort to get to, or it may be that you need to synchronize power consumption along with other digital signals. So there may be some form of reset, enable, or feature trigger as a digital signal that is very useful to look at along with the power to understand what's happening. So one of our customers, for example, on the bottom left of this slide, wanted to test their ASIC, their chip that they had developed, and on their R&D test board, they had 3 power rails going into that. Fortunately, they had the good idea to put 0 ohm resistors, so shunt points, on each of those power rails. However, the regulators are on the board to generate those 3 power rails, so there's no simple way to tap into them. But we have 2 solutions to that. One is to remove the shunt resistor and wire through the module on the top, so we can put multiple rails through and out of our power analysis fixture, and we can then tap into them, measuring both voltage and current in real time. We can also wire in a similar way into any digital signals you need to capture. However, some customers will put embedded shunt resistors on their board. So if you replace a 0 ohm test resistor with a known resistance of shunt resistor, we can then, using an external shunt fixture, we can tap into either side of that, and we can then calculate the current and voltage across it, and therefore give you the power again. So these are ways of getting energy consumption figures from within a test board. The third one, again, AC motors are very common these days. So power efficiency, key question. Peak current, what do you need to be able to supply to it? These devices tend to have quite a complex current, voltage, and frequency profile. So being able to capture that all together is very useful. And then, of course, we've got the question of failures, either instantaneous ones or degradation over time. Being able to look in detail at high resolution at what your device is doing gives us a really good insight into how it is wearing and changing. Once you've decided what you're trying to capture, the next question is, well, how fast do you need to sample? How much data do you need to sample? And a key thing for us to think about is that fast sampling is not always going to be better. What do you need to capture? So are you trying to capture noise, high frequency noise, peaks, which require fast sampling, or is it longer term profiles and trends? In which case slower sampling is normally fine, but a larger memory capture is more important. Next is, well, do you know when the capture event that you want will happen? If yes, or you can provoke it to happen, then a short capture depth is fine. If you don't, you may want to be able to capture for minutes, hours, or even days until you can be certain that you have captured the data you need. Next, how many rails? Single rail or multiple? And again, do you need to sync that up with a digital signal that might help you understand what's happening? And then a really important one is, how simple is your power test setup? The more complex it is, the less accurate it is, simply because mistakes are likely to be made. And we have, in many cases, seen customers in the data storage industry come back to us and say that they've measured something on a scope and they get a different result than we do. And in the significant majority of the cases, it's just because the oscilloscope has been set up incorrectly, or for instance, a voltage probe has been put on the wrong point on the boards. It's really easy to do, but a simple setup is both less likely to cause errors, and it can also be safer, especially when we're dealing with AC systems. If we can avoid putting voltage probes directly onto exposed metal, it's going to be a lot safer. So we recently, as an example, did quite a bit of work with SNIA, the Storage Network Industry Association, as part of their new energy efficiency specification for SSDs. And one of the things they wanted to know was, how fast did they have to sample to get accurate power results? So our base sampling rate in this test was 250,000 samples per second, which is a 4 microsecond sampling window. So that's our 0 point. And if we go down the graph, the bottom chart from there, we can see that at 8 microseconds, we then got to less than 0.06% error, which is tiny. However, quite a jump. When we move to 16 microsecond sampling, we get almost a 7% error rate, so it's going into the red range. Now that's clearly not good. So we get this very rapid increase in errors below a certain sampling rate. But then if we go up, 250, 500, 1 mega sample, we're really in the noise. Each test is different slightly by random variability. There is no benefit in sampling faster whatsoever. And quite often we'll have customers go, well, we need at least a mega sample, 1 million samples per second. And in most cases, the answer is you probably don't. But what that will do is fill up your memory very quickly, and it may not let you capture the length of data that you require. So there are many different ways of capturing power. And on the right-hand side, going from the bottom up, we've got a simple watt meter that you could buy on Amazon for a few dollars. It will give you a basic uncalibrated indication of AC, but nothing more. But that can still be very useful, and it's very simple. Next, we've got a multimeter. We've got a picoscope, which is a fairly cheap PC-based oscilloscope. Next up, we have an expensive power analyzer, and then a high-end oscilloscope. So there is a huge range of money that you can spend on different pieces of test equipment. And the key I would recommend is to look at, again, what are you trying to capture and how simple is it, and choose equipment that gets you the data you need in a way that is easy to capture, reliable, and doesn't cost more than you require. So to look a bit about Quarch, what do we do differently? And one thing is that wherever possible, we do plug and play fixturing. So if you look at any high-end AC power analyzer, for example, it will have a number of ports on the front to add voltage probes and current clamps. So we've got a different route. We have, on the left here, we have standard IEC connectors for 110 and 240 volts AC. And we have larger standard connectors up to 63 amps, three-phase AC. But in both these cases, a junior engineer can come in, plug the connector in on both sides, set up in a few seconds, and start capturing power data. There's effectively no risk. These are standard connectors. There is no need to get to exposed surfaces. There is no need to customize cables or attach current clamps. And we do a very similar thing, for example, for automotive SSDs. We have a fixture that goes between the SSD and the host. You plug it together in a few seconds. Your system will otherwise run exactly as it did before, except that we can now capture the power data. And all right, let's start capturing data. So this here is a little example captured with our system. This is a 10-second capture of a hard disk spin-up. But the interesting thing here is, well, first of all, you need to be able to see the data. So to understand what's happening in many cases, so that's going to be an oscilloscope or a Quarch device or similar. But on an oscilloscope, you quite often have a limited capture depth, you have a limited ability to control it, and we frequently find customers will take a picture of the scope with their phone and send it round. It's not an ideal way to share data. In our case, the software is running on a PC, and we can take this large trace and we can zoom right into the smallest part of it. In this case, we're looking at a 200 microsecond period of voltage ripple that's caused by the physical movement of the hard drive's head. Zooming into that from the larger trace took a couple of seconds of clicking on the main screen. It's very simple to navigate the data, and that makes it easy to find what you're looking for. The next case is long-term recording. So we allow you to record for hours or days. So this example here is a 30+ hour trace. It was fully automated using a simple Python script, which has run, I think, in the region of 50 different workloads on an automotive SSD. And each one of these workloads, lasting a few minutes, is individually annotated, again, from the script. We even have the ability to bring in custom user channels like megabytes per second for throughput or temperature, so you can see how your device is responding along with the power consumption. You can combine the data together. So in this case, we have an SSD that we are asking to go through its different power states. So at the beginning here on this first section, this is its fully active power state running as fast as it can. The purple line is the amount of data going through. In the second section, we have asked it to go into a slightly lower power state. We see the power come down, but we also see the performance come down as well. And in the third case, we ask it to go lower again. Again, we see the performance come down. We see the power dip quite a lot. One interesting thing here, though, is that the efficiency of the device at moving data, so the megabytes per second per watt, is actually poorest at the low power state. So yes, your device will use low power, but the performance will be dreadful in comparison. That can have a significant effect on the user, even if you're trying to save power. Another interesting problem with this device test is that we found that on the right-hand side of this graph, there was supposed to be more interesting data as we told the drive to go into its power-saving sleep modes, but it didn't do so. It claimed it did. The host system believed it was in a sleep state, but in practice, the drive was still consuming, actually, if we look here, it was consuming more power in its sleep state than it was capable of when it was actually running at times. So the combination of this host and SSD did not sleep properly, meaning it would use significantly more power idle than you would expect. No, it's not always about looking at the traces, though. We can also pull out detailed statistics. In this case, we're pulling out statistics between every single one of the annotations we dropped, so for each of the workloads. And then with a single click, we could look at, well, what is the worst case power consumption? What is the best case power consumption, and similar. Make it very easy to run automated tests overnight and come back in the morning and get a large amount of high quality, easy to interpret data on what your device is doing. We've spoken a couple of times about this idea of having digital signals and power consumption together. And this is one of them. This is a PCIe storage device powering up. So we have the current trace in blue, and at the bottom we have the reset signal, which is used to tell the device to wake up or reset. And the interesting case here is that the reset signal has been asserted 1, 2, 3 times. I've marked with an arrow. Now that may not matter a huge amount, but there is a question as to why did we need to reset a device 3 times on startup? That will slow down the time until it's ready. That will, for instance, if you're in a vehicle and you've just switched it on, it will take longer until the drive is ready. It might only be a second or two, but it does make a difference. And being able to see these digital signals along with the power gives us more information on what's happening. Being able to see stuff live also is very useful. So this is a live capture in Quarch Power Studio of a storage device. We basically hit record, turning the power on, and we can see in real time the power up. And this is really nice that you can look in real time, but still, while you're capturing, zoom in on other things and see what's going on. So it's very easy to use. And our aim is to put an order of magnitude more power data in front of your engineers without overloading them, but that lets them make better choices over designs, over this selection of devices to integrate and similar. So, any questions, Pratibha?
Yeah, coming up. So some of the questions we had around, I mean, I'm aggregating the questions. I'll make a list of them and we'll go one by one. We had questions about if we have multiple power rails, then how do we address it? Can we cascade all of them together?
So the largest number of power rails that we do at the moment is 3-phase AC and 4 channels of DC. It would be possible, however, to use 2 different power devices together, capture them, and then merge the traces together. So it's not quite a neat a workflow, but it would be possible to do.
Okay. And there's a question about, do we support single phase, 3-phase, and what is the maximum minimum voltage current monitoring we do?
Sure. Yeah. So on AC, we support single phase and 3-phase. I believe the maximum current that we do is 63 amps per phase and 400 volts.
Okay.
We have there's details on the data sheets as well. So if anyone is interested, drop Pratibha and her team a message, and we can get you more information.
Sure. And another set of questions is all about download. What is the storage capability of? I mean, we showed about hours and days of capturing the data. So there's question about storage capability, streaming capability, and then can they export the reports? Do we have any useful tools to address any charging standard specifications? That's one question about all of the reports and traces we've generating.
Okay, so in terms of storage, so our software runs on a PC, meaning that the storage limitation is how much space do you have in your drive. So we can easily capture a 50 gigabyte, 100 gigabyte trace if that's what's needed at high resolution. In terms of exports, you can export the raw data into a CSV form for post-processing. You can export the statistics tables, you can export images, you have full access to all the data in its entirety, either via the software, clicking the buttons, or via the automated interface.
Okay, thank you for that, Andy. And then final question we have about this is, what is the high voltage isolation we provide, and whether we have any end-of-line testing solutions for EV chargers?
So we don't provide end-of-line testing. We do use end-of-line testing. So all of our AC devices are tested for the integrity of their ground and for isolation. But no, at the moment we only supply the power measurement equipment.
Okay. We'll run the poll now, Andy, before we step into the next session.
Sure.
Yeah. The poll question now we have is, how automated is your current testing workflow? Whether it's fully automated, mostly automated, partially automated, and mostly manual. Yeah, we have participation for the poll.
That's great. We got
Yeah.
a real spread again.
Yes.
Yeah, and everyone's even a company that does a huge amount of automated testing, individual engineers will end up with a lot of manual things sometimes. So the more automation that we can provide and make simple for individual engineers, the better your lives will be.
Okay. So I think we can end the poll. Okay. So we have about 35% who say it's mostly automated, about 30% who say partially automated, 23% who say fully automated, and about 13% who say it's mostly manual. Yeah.
Awesome. So we will talk a little bit more about automation just in the last bit, but for the moment, let's have a quick look at USB testing. So USB is very common in a vehicle. We have a number of devices that are intended explicitly to address that. So here's one. This is a USB switch. So this is an 8-to-1 physical layer switch. The aim of this is that you can plug one port into your infotainment system. You can plug 8 different devices into the 8 different ports, and then one device at a time can be connected to the host. The other devices are fully isolated. So what this means is it is the equivalent of removing one device and then separately plugging in a second. It does exactly the same. That allows you to, of course, instead of sitting there testing many different phones, flash drives, dash cams, or similar, it allows you to automate the system. It allows you to automate hot plug as well, removal and insertion, to separately isolate USB 2 and USB 3, so you can test the difference on what the effect of different supporting cables may have on individual devices as well. So this is a great way to simply improve automation around USB. Now, if you're interested in more focusing on one device and what it does, we can then look at one of our breaker modules that are designed specifically for USB. So we've got USB 3, we've got USB-C. So these allow you to automate a wide range of physical layer tests around connection and failure. They are basically the same idea as the automotive multi-protocol breaker we looked at earlier. They're just explicitly designed for USB. So we can do connect and disconnect. You can automate the removal and insertion of a USB device. You can plug it multiple times without having to be there. You can simulate the difference between fast and slow hot plugs. You can simulate the effect of someone wiggling the cable into the connector instead of plugging it nicely. We can do corner case tests where we deliberately do unusually fast or slow hot plugs to make sure that the device will always enumerate correctly. We have individual control of every non-ground pin on the connector. So that includes VBus, the USB 2 differential pair, and the high-speed transmit and receive pairs. And on those high-speed signals, we can inject data errors again down to 50 nanoseconds, so we can simulate bad cables and bad links. Again, anything that the hot plug is important. Now, in a data storage system, hot plug is essential because people frequently hot plug devices and cables while the servers are running. It has to work every time. It's not as important in a vehicle if your phone doesn't connect perfectly every time, if you have to unplug it and plug it back in again. But it's not fun for the user. There is the potential of faults that then ripple through the system and might crash the infotainment, for example, which will then annoy them even more. So these are certainly things that you want to test well before vehicles get into customers' hands. On the power side, again, with higher power charging standards from USB-C, with faster charging phones, verifying charging speeds and debugging power problems can also be very useful. So we have a power analysis fixture specifically designed for USB-C. We can capture, again, 250,000 samples per second with long-term capture. This is a calibrated, proven device, which is used in many cases based on our enterprise M.2 power analyzer. So this is not a cheap tool that you buy off eBay, but it will also give you far more accurate and more useful data. And at the bottom right there, we've got an example of a USB charger connected to a phone, and we can see the big spike of inrush current here actually disrupts the ramping of the power rail. There are many interesting things that we see when we start looking at these traces. Again, I'd strongly recommend that if you're implementing high-speed charging on your vehicles. So how would you actually get started with any of this testing if it's of interest? And that is fairly easy. Our regional resellers are skilled partners. It's ESA that we have on the line today. They will be able to provide local support and logistics. They will be able to provide evaluation kits. So there's a risk-free trial if you want to try something out. In terms of technical support, there is direct access to the Quarch engineers in the UK by phone and by email as well when it's necessary. We can do on-site training and support by negotiation. We maintain our products for the long term. Even outside of warranty, we frequently repair products that are 10+ years old. There may be a cost for that, but it's not expensive, and we stand behind our products. Now, there were questions on automation. We provide a simple Python package. All of our software, such as Quarch Power Studio, is also available as a full download. It's not cloud linked in any way. Once you have it, it is all yours, and it's yours indefinitely. So regardless of what we choose to do in the future, you will always have full access to any features that you bought. We price by selling the hardware. Our software, our automation tools are all included. We have many automation examples on our website. And our software engineers are happy to give you some tips and hints to get you started, or even to help develop tests in some cases, especially if we think they'd be useful to others. Just a little Python example here, using half a dozen lines of code to run a power cycle on a communication link. It is very simple. If you prefer not to use Python, then we have open interfaces, both in terms of Ethernet, USB, and serial that you can use. Basically, if you can open a port, the vast majority of our commands are simple, human-readable text commands, making it very easy, again, to write scripts and very easy to automate into different systems. And I think that takes us pretty close to the end. The next steps, clearly, if you're interested in a quotation, a data sheet, evaluation, a discussion, Laurie and I will be in India in a couple of weeks. If there's anyone that is keen to meet and we have time, we'd happily do so. If that's a bit too soon, we can discuss it another time.
Yeah. So some final questions we had was that they asked us about evaluation units. Andy just answered the question. We have all of these evaluation units available to us, available here locally. We can send it to you. We have regional offices across the country. Most of you know us. So all of that can be arranged. And a few of you were asking about the deck. We will surely share the deck with you, and if you need the recording, we will send it to you. That's all from us. Thank you, Andy, for today's session. Thank you, everybody, for spending the time with us to learn about Quarch Automotive Solutions. We're very pleased with all the interest. Like I said, evaluation units are all available. These are all free. We look forward to working with each of you in your automotive test initiatives. Thanks to everybody once again. Thank you for everybody on the Quarch team and for the ESA team for making this happen. Have a great day ahead. Thanks and bye-bye.
Thank you, Pratima. Thank you all. Bye now.
Bye.